All right, now let's find the nth term of this geometric sequence, 10, 9, 81 over 10, 729 over 100. And let's find the ninth term of the sequence and then find a recursive formula for the sequence. All right, so 10 goes to 9, which goes to 81 over 10, which goes to 729 over 100. So it looks like every time we're dividing by 10 and multiplying by 9. So it looks like the common ratio is going to be 9/10. We'll multiply by 9 and divide by 10. If we wanted to find that, remember you can take a term divided by the previous term, and so 9 divided by 10 would give me 9/10. So that's going to give me my R. And then that's my R, and my first term is 10. So the formula for my explicit formula for my geometric sequence would be a sub n equals the first term times the common ratio to the n minus 1 power. So in this case, it's going to be 10 times 9/10 raised to the n minus 1 power. So that is going to be my explicit formula. And then the ninth term in my sequence would be a sub 9 equals 10 raised to the 10 times 9/10 power raised to the 9 minus 1 power, so raised to the 8th power. And so if I were to do this, we're going to do 9 raised to the 8th power. And so we get 43,046,721 over 10 to the 8th, and 10 would make 10 to the 7th, so, and then 10 to the 7th power, and we would get 10 million. So without reducing, we would get 43,046,721 over 10 million. And that would be the ninth term in that sequence. And then find a recursive formula. Well, to find a recursive formula, you take the previous term. So you're going to take a sub n minus 1, so that'll be the previous term, times the common ratio, so 9/10. And so that would be my recursive formula for the sequence. Take the previous term times the common ratio, which was 9/10 in this problem. All right. To find the sum of a geometric sequence, just like we wanted to find the sum of an arithmetic sequence, we have our own formula. So the sum is you take the first term times 1 minus the common ratio raised to the nth power divided by 1 minus the common ratio. So that's your formula for the sum of the first n terms of a geometric sequence. So find the sum of the first n terms of the sequence 1/2 n. So we are going to find the sum. So our sum is going to be the first term. And so if I wanted to find the first term, I would plug in 1. So this would be 1/2 raised to the first power, which is just 1/2. So I'm going to take the first term times 1 minus the common ratio. Well, if I found my second term, I'd take 1/2 raised to the second power, which would be 1/4. So to go from one term to the next, I'm multiplying by 1/2 each time. So my common ratio is 1/2. So 1 minus 1/2 raised to the nth power over 1 minus 1/2. And so without simplifying, that would be the sum of the first n terms of that geometric sequence. All right, let's find the sum of the first 15 terms of 1/3 raised to the nth power. So let's find the first term. So the first term is going to be 1/3 raised to the first power, which was just 1/3. The second term would be 1/3 raised to the second power, which is 1/9. So the common ratio to move from one term to the next, my common ratio is 1/3. So my first term is 1/3 and the common ratio is 1/3. So the sum of the first 15 terms is going to be you take the first term times, then we're going to do 1 minus 1/3 raised to the 15, because we want the first 15 terms, and then divided by 1 minus 1/3. All right, so let's do this. So we're going to do parentheses 1 minus, and then 1/3 raised to the 15th power. I bet I have to put 1/3 in parentheses. Raised to the 15th power. And then divided by 1 minus 1/3. And then I'm going to multiply that by 1/3. And so the sum of the first 15 terms of this sequence is going to be 0.4999999. And so we're going to say it's approximately a half, or 0.5. So the sum of the first 15 terms of this sequence would be approximately a half. And so just be careful on your graphing calculators that you're having parentheses around the correct items in order to do the sum correctly. All right. So will a geometric sequence, when you sum it, converge or diverge? So converge means that the sum will equal a finite number. Diverge, that the sum would equal an infinite number, meaning that it wouldn't become finite. The sum would be infinity or negative infinity. So for a geometric series to converge, the common ratio needs to be somewhere in between -1 and +1. So if your common ratio is somewhere in between -1 and +1, then the geometric series, when you find its sum, would converge. And its sum would be you take the first term divided by 1 minus the common ratio. So if you're going to add up all the terms in that sequence, so you're going to go from the first term to the last term, and the last term would be the infinite term, then its sum would be a sub 1 over 1 minus the common ratio. So the sum of an infinite number of terms in a geometric sequence would be you take the first term divided by 1 minus the common ratio, as long as the common ratio is between -1 and +1. All right, so determine whether the geometric series 2 times the quantity 2 over 3 raised to the k minus 1 power, which is 2 plus 4/3 plus 8/9 plus ... forever and ever, converges or diverges. So we've got to find the common ratio. So remember, to find a common ratio, you can take a term divided by the previous term. So we can take 4/3 divided by 2, which would be 4/6, which is 2/3. So the common ratio is 2/3, which is in between -1 and +1. So this is going to diverge because the common ratio's absolute value is less than 1. And then to find the sum of the infinite number of terms, remember, you take the first term divided by 1 minus the common ratio. So in this case, the first term, plug in 1. So this would be 2 times 2/3 to the 1 minus 1 power, which would just end up being 2, which makes sense because they gave it to us. So the sum of the infinite number of terms in this sequence would be 2 divided by 1 minus the common ratio, and the common ratio is 2/3. So this is going to be 2 divided by 1 minus 2/3 is 1/3. So the sum of this sequence of numbers, the series 2 plus 4/3 plus 8/9 plus continue forever and ever, would be 6. It's a finite number, and it's 6. All right, so let's use the idea of a geometric sequence or series in a real-world type problem. So initially, a pendulum swings through an arc of 18 inches. See figure 9. So we've got a grandfather clock, and the pendulum is swinging 18 inches to go from left to right. On each successive swing, the length of the arc is 0.98% or 98% or 0.98 of the previous length. What is the length of the arc on the 10th swing? So this is going to be a geometric sequence because you are multiplying by 0.98 to get to the next length each time. So you're going to take the first term times the common ratio to the n minus 1 power, and that's going to be our explicit formula. So our first length is 18 because that's how long the first swing is. The common ratio is we multiply by 0.98 to get to the next length and then to the n minus 1 power. So for part A, it wants to know what is the length of the 10th swing. So the length of the 10th swing is going to be 18 times 0.98 raised to the 10 minus 1 power. And so now if we go on Desmos and we evaluate this, this would be 18 times 0.98 raised to the 9th power. And so the length of the 10th swing is going to be 15.007 inches. On which swing is the length of the arc first less than 12 inches? So we want 12 to be greater than 18 times 0.98 raised to the n minus 1 power. So we want to figure out when this works. Well, let's see when it's equal to 12. And then we want one swing more than that. So to solve this, we're going to divide both sides by 18 to get the exponential expression by itself. And so 12 divided by 18, we get points, well, we get 2/3. So 2/3 equals 0.98 raised to the n minus 1 power. And so now let's write this as a logarithm in order to solve. So it's going to be log base 9/8 of 2/3 is going to equal n minus 1. And so now we can evaluate this. And so remember, you take the log of the product. So we're going to take the log of 2/3. And then we divide by the log of the base, 0.98. And so we get 20.069 equals n minus 1. So add 1 to the other side. So 21.069 equals n. So on the 21st swing, it's almost 12 inches, but we want it to be less than that. So for part B, we need 22 swings. So if the clock swings 22 times, then the arc should be less than 12 inches. So let's make sure that that actually worked. So what is the 22nd swing? So we would take 18 times 0.98 raised to the 22nd swing minus 1, so 22 minus 1. And so if I did this on Desmos, I would get 18 times 0.98 raised to the 21st. And we get 11.77, which is less than 12. So on the 22nd swing, the length that the pendulum swings is 11.77. Well, if we did one more than that, 20th, that's more than 12. So it has to be the 22nd swing. On the 21st swing, it's still more than 12. So on the 22nd swing, it's less than 12 inches. For part C, after 15 swings, what is the total distance the pendulum has swung? So we want the first swing plus the second swing plus the third swing plus the fourth swing, et cetera, et cetera. So for part C, we want the sum of a geometric series. And so remember, the sum of a geometric series is going to be, you take the first term times 1 minus r to the n divided by 1 minus r. And so the first term, so we want the sum of the first 15 swings. So we're going to take the first term, which was 18, times 1 minus, the common ratio is 0.98, and then raised to the 15th power, divided by 1 minus 0.98. And so if I did this, I would get 18 and then times, and then parentheses 1 minus 0.98 raised to the 15th, and then divided by 1 minus 0.98. And we get the total distance that the pendulum has swung over the first 15 swings is 235, and we'll just say 0.3 inches. When it stops, what total distance has the pendulum swung? So we need to figure out when the distance that the pendulum travels is 0, and then figure out how many swings that took, and then we'll find the sum of the geometric series. So for part D, we want the distance to almost be 1. So we want when 0 equals 18 to the 0.98 raised to the n minus 1 power. So divide by 18. So we want to know when 0 equals 0.98 raised to the n minus 1. So if we put this in log form, log of 0.98 raised to the 0th power equals n minus 1. Well, remember, log 0 doesn't exist, so we're going to make this as small as possible. So we're going to make this like 0.000000001, and then we'll do that on Desmos. So we'll just make this as small as possible. So we're going to do log of 0.000000001, and then divided by log 0.98, and then we'll add 1 to that. So it looks like it's going to take about 1,254 swings for that distance to be almost 0. So 1,254 swings. So now we want the sum of the first 1,254 swings. So that's going to be the first term, 18, times 1 minus 0.98 raised to the 1,254 divided by 1.98. So let's figure out the distance that this guy has swung. So 1 minus 0.98 raised to the 1,254th power. And then, whoops. And then divided by 1 minus 0.98. And then we're going to times that all by 18. And so it looks like the total distance that this would travel would be 900 inches if we round it up. Now, will the pendulum ever stop swinging? Since it's an exponential, it'll never actually reach a distance of 0. And I mean, it will eventually stop swinging. If this was a frictionless environment, it wouldn't. But we could also think of this as the sum of an infinite series. And so you would take the first term divided by 1 minus the common ratio. So another way we could do this, if we wanted the sum of the first or the infinite number of swings of this pendulum, you would take the first swing minus 1 minus the common ratio. And we should also get 900 if we do it this way. So let's take 18 divided by 1 minus 0.98. And notice we get 900 if we did an infinite number of swings. So it'll work either way. All right, so annuity. So suppose P is the deposit in dollars made at the end of each payment period for an annuity paying I% interest per payment period. The amount A of the annuity after N deposits is given by the final amount is equal to your principal times 1 plus the interest raised to the nth power, which is the number of payment periods, minus 1 divided by the interest. So for example, to save for retirement, Brett decides to place $4,000 into an individual retirement, an IRA account, each year for the next 30 years. What will be the value of the IRA when he makes his 30th deposit? Assume the rate of return is 7% per compounded annually. This is the historical return rate of the stock market. So his final amount is going to be what he puts in every year. And so he's putting in $4,000 every year. And so it's going to be plus 1 times the interest rate, so 0.07%, raised to the number of deposits. His number of deposits, it's going to be 30. And then minus 1, and then divide by the interest rate, so 0.07. So at the end of 30 years, he'll have 4,000 times, and then we have 1 plus 0.07 raised to the 30th, then minus 1, and then divide, well, I guess it really doesn't matter. Let's do... and then divided by 0.07, and we get $377,843, and we'll round that up to 15 cents. So at the end of 30 years, if he deposits $4,000 and it's earning 7% interest, at the end of those 30 years, he'd have $377,843.15. If we just took the $4,000 that he's investing times the 30 years, you would get 12, and then 1, 2, 3, 4. So he would have $120,000 if you just took his $4,000 30 times. He would have $120,000 that he invested, and he ends up with $137,843 with that interest that he's earning in his IRA. Let's look at another example. To save for her daughter's college fund, Miranda decides to put $100 aside every month in a credit union account paying 2% interest compounded monthly. She begins this savings program when her daughter is 3 years old. How much money will she have saved by the time she makes her 180th deposit? How old is her daughter at this time? So her final amount is going to equal how much she invests each month. And then it is 1 plus the interest. So 1 plus her interest is 0.02, so 2%. and then raised to, we're going to do 180 deposits, and then minus 1, and then divide by the interest, so 0.02. And then she is investing $100 each month. All right, so now if we go on Desmos and do this, we would get 100, and then times, and then parentheses, 1 plus 0.02 raised to the 180th power, then minus 1, and then divide, well, I guess that won't really matter, 0.02. And so she will have $171,604.16 at after her 180th deposit. And it wants to know how old her daughter would be. Well, if you take 180 divided by 12, 15 years she's been depositing by. So her daughter was 3 years old, so her daughter will be 18 years old after 180 deposits. And so she's invested $100 every month. So every year she's invested $1,200. And for 15 years, she has invested a total of $18,000. And that $18,000 is now worth a total of $171,604.16 at the end of 15 years. All right, your homework is 12.2 and 12.3. Let me know if you have any questions.